So welcome everybody. A new season of Montréal MLOpt begins today, and we are very happy to have our very distinguished colleague and my dear friend Dimitris Papailiopoulos, assistant professor currently at Wisconsin-Madison, also my classmate at the Technical University of Crete many years ago. So Dimitris has done all sorts of work, ranging from information theory and coding theory, things like that, telecommunications before that. But now he's doing some very interesting work, which is the topic of today, on connections between pruning and some very important questions in CS theory. Okay, the complexity of subset sum and some very nice results in this area that will give us an idea about what's happening behind this lottery ticket hypothesis, one. And number two, it'll basically give us even tighter bound on how much of a parameterization we need in order for pruning to result to learning. Okay, this is my introduction.
Thank you for the very kind introduction and for the invitation to present to you here. Yeah, I'll just talk to you a little bit about some of the recent research that my group has been doing in the area of pruning, but not as a means of sparsification, more as a means of learning a function. Yeah, this is kind of like the neural network equivalent of a quote by Michelangelo, where you start with a random big block of stone, and the work of the sculptor is to basically discover the statue inside that big block of stone. So let me just take a step back and tell you a little bit about pruning. I'm sure everybody here is familiar with sort of the basics of pruning. It started very early. It's an idea that originates in the early 80s. The idea of pruning is that basically you kind of like start with a wide network. These days, we have hundreds of millions of parameters. And we do this for many reasons. Over-parameterization is a good thing with regards to optimization and other reasons. But with regards to the efficiency of those networks, you would like them to be sparser, right? So you want them to be sparse because sparsity is associated with less energy during inference, less compute, and less memory, potentially, right? So that would be what we would like to have. There is kind of like a very general meta-algorithm for pruning networks, for cutting the edge, for making those things sparser. You randomly initialize them, and you get your random initial network. You train them with SGD. And once you train them, you start cutting some of the edges. How do you cut them? Well, you prune them according to maybe, the magnitude of those edges. So maybe you keep the most important ones according to magnitude. Once you do this, you will experience some loss in accuracy, and you can fix that by retraining. The effect of retraining, however, is that the network may become dense again, and you kind of like have to reiterate this process of sort of pruning and retraining to full accuracy. And I just want to take a quick pause here to see if there's any questions. I mean, this is a very high-level idea of not all of the pruning algorithms ever, but I would say a big majority. So I'll just take a 5-second pause here to make sure everybody's on the same page. Yanni, by the way, can you tell me whether you can see the pointer? You should, right?
Absolutely, yes. We can see your
Okay.
pointer. And
cool.
Yes, there are no questions right now. You can proceed.
All right. So the main issue with this kind of like prototypical algorithm for pruning is that you have to train to full accuracy once, right? So you have to like use the dense network and train it to full accuracy, and then you do the pruning, right? So this is expensive, and the question is whether you can avoid this computationally expensive step. And this is where the lottery ticket hypothesis begins. This sort of started from a paper in iClear 2019 that in fact also won the Best Paper Award. So Jonathan and Michael, what they said is that they conjecture that without having to train to full accuracy, you can find sub-networks that are sparse at the beginning of training, at initialization. And if you somehow magically can find those networks, if you win the lottery, the initialization lottery, then you can train them just once to full accuracy. So you basically can skip this sort of initial training phase and have a network that's very sparse and kind of like train this thing once, right? So this is, what was postulated in the original lottery ticket hypothesis. I put a little asterisk here because this is not quite true. We'll come back to this, but that's kind of like the main idea, that at initialization, there exists sparse networks that you can train to full accuracy.
Dimitri?
Yes.
So here we have a question that might be relevant. So let me ask a clarification question of my own. So lottery ticket hypothesis is what's described at the top of your figure.
Correct. Yeah.
Right?
Yeah.
Okay. Somehow you win the lottery, which means you start with a right sparse network, and then you just train it once and you're done.
Right, and the weights are also important, right? So you initialize, and then there's a subset of those weights that you can just train once, and you could achieve the same accuracy as if you were training a fully dense network.
I see. And the question that we had in the chat is very much related to that, and it was basically when you were talking in your previous slide before you went to the lottery ticket hypothesis, it was why not initialize with a sparse network instead, right?
Yeah, so that's a good question. So generally speaking, so this is a complicated matter, and it's related to the initial pruning literature, but also to the lottery ticket hypothesis. If I were to just randomly sample a subnetwork from the architecture, initialize it with random weights and train that definitely has smaller accuracy than doing either the first thing, kind of like the pruning and retraining, or using the lottery ticket hypothesis algorithms that I will talk about. So basically, somehow overparameterization is extremely important in the beginning to find the sparse network. And if you were to just throw away all that, all those extra weights, that would not help. But that's a very good question. That's the most meaningful thing you can ask, right? Why we don't start with a random subnetwork? But that does not work.
Okay, thank you.
Okay, good. So so I have an asterisk here. I'll explain what that means. But the main question. So first of all, if you could win the lottery for free, that would be a big deal because you could avoid this whole training, the dense network, and then pruning and retraining. And the question is, how do you win this lottery, right? Is it possible to win the lottery? They suggest an algorithm. So Jonathan and Michael suggest an algorithm in the paper. The algorithm is called IMP, or iterative magnitude pruning. So what they do is basically very similar to what people were doing, before the LTAs, which was to, you start from a random network, you train for a small number of iterations, maybe, I don't know, like one epoch. You keep only the 1% highest weights or largest weights. And then you keep that architecture, like you throw everything away, and the values that you assign to those weights, you roll them back or you rewind them to the initial values, okay? So then that corresponds to a network from the initialization that has a particular architecture that this IMP algorithm found, okay? And there's a lot of hyperparameters. How much should you run this? What's the percentage of weights? How many rollback cycles you should do, and so on and so forth. So there certainly is a cost to winning the lottery. And the asterisk that I put here is that, in fact, we know from later literature that this doesn't always work. So it's extremely hard to find, or impossible, as you say, to find subnetworks at initialization that you can only train once. You actually need to do a little bit of a warm-up period before you kind of like find this subnetwork. So take this with a little bit of a grain of salt. But the main philosophy is that you can, for the largest part, avoid training a fully dense network to full accuracy. So that step for sure you can avoid. So again, a quick pause here to see if everything makes sense.
There's a question from Nicolas. Go ahead, Nicola.
Yes, hi, Dimitris. So about the prune, or the value of P, the percentage of the weights that you prune, this is something that you need to tune every time, and how you select this percentage. Is it random or is it deterministic?
So if this was random, this wouldn't do much, right? Because you do have the rewinding to the original weight. So it has to be informed by some type of an importance metric. People just normally either use, how big the weight, like, the absolute magnitude of the weights, or how much the weights changed during whatever that training period. What was the other question? Yeah, so the P percentage is a hyperparameter, right? And in fact, these 2 to 5 can be repeated multiple times. So, you train for a little bit, you throw away, let's say 50% of the weight, so you have 50% sparsity, you roll those weights back to initialization, train them again, throw another 50%, so now you're at 25% sparsity, and so on and so forth. So, P is a hyperparameter, and you do have to choose it beforehand. Yeah.
Okay.
I mean, I guess you can decide it later too. It's not. There's no principle, I guess, here, but yeah.
And the weights that you prune in the first step remain pruned for the remaining steps, correct? You cannot.
Once they're out forever. You never touch them again.
Okay. Thanks.
All right. Very good. So going back to the first question. Random subnetworks don't work as well as lottery tickets. There is some magic to those subnetworks. So being careful about how you initialize makes a big difference. And they ran some experiments. The first paper had mostly on MNIST, and they find that SGD on random nets is just worse than compared to like training lottery tickets. And it's not just the architecture. The choice of weights matters as well. So if I were to basically take the architecture, the subnetwork that IMP returns without the weights, and I were to reinitialize those weights to whatever random Gaussian, that does not work. So it's a combination of the subnetwork and the weights that matters a lot. And these findings stirred a lot of interest, and there's been a ton of research that has happened lately in this lottery ticket hypothesis literature. And again, the current status or the state of the art is that you can find good sparse subnetworks early on in training, like, at 1%. So you train 1% dense, and at that point, you can find sparse subnetworks that can only be trained once to full accuracy. But you can't do that at initialization. So that original claim is not true across every network, but it is definitely true as long as you do a little bit of warm-up.
Dimitri, we have a little clarification question here. When you talk about original weights and rolling back to the original weights, can you repeat exactly what that was?
Yeah, sorry. By original, I mean the initial. So you sample everything Gaussian or whatever you want. You train for a little bit. You keep the top 10%, let's say, of those weights. And this is a subnetwork now, right? Everything outside of this support of top 10% weights, you kill forever and never going to be part of training anymore. And this subnetwork, you don't keep the weights that it currently has. You rewind those values back to the initial weights. So that's, yeah.
Okay, thank you.
All right. Okay, so this is about the lottery ticket hypothesis and kind of like the idea of, pruning early in training rather than having to wait at the end. And there's been a lot of literature trying to understand this from a theoretical perspective and a geometrical perspective, and what is it about the loss landscape and the geometry of the problem that allows sort of this phenomenon to exist. For me, one of the most interesting kind of findings across this literature is that you actually may not even need to train. So pruning may be enough to find a good subnetwork that works well. So let's see what I mean. There was this paper by Ramanujan and Wartzman et al. That appeared in 2019 at CVPR that was called "What is Hidden in a Randomly Weighted Neural Network?" And this is what these folks basically did. Which it's one of my favorite papers from the past, I'd say, 5 years. And they found the following. So they're like, okay, the LTH tells us you start with a network, you initialize, and you win the lottery somehow. And then you just train this sparse subnetwork to full accuracy. What these folks were saying, which from now on I will call the strong lottery ticket hypothesis, or the pruning is all you need hypothesis, is that instead of starting from ResNet 18 or whatever architecture you have, take a wider version of that network. So over-parameterize it a little bit more, randomly initialize it, and what you can do or what these folks found experimentally is that you can find subnetworks of this wider network that basically have the same accuracy as, a state-of-the-art train network for, whatever given dataset and predictive task they cared about. And I will clarify this in a little bit. But kind of the point is that this strong lottery ticket says that you don't even need to tune the weights. You can find subnetworks at initialization with random weights that perform perfectly well, okay? And I just want to make a note here that there's a big difference between the two literatures. The original LTH and pruning literature targets sparsity, so sparsity is important. And what comes out of those algorithms is like, networks that are like, 10% sparse or whatever. The strong LTH does not care about sparsity. It studies the ability to learn or to, train neural networks essentially without tuning weights, just by pruning. So sparsity is no longer a goal here, but it can sometimes be achieved as a side effect. But kind of the main point that I will like to study now and kind of like walk you through is this idea of learning by pruning. And again, I want to take a few seconds pause here just to make sure that everybody is on the same page.
Any questions from our audience?
Okay. So let's see. So basically, this is what they saw in this paper. So they say we have an algorithm that basically does kind of like the equivalent of gradient descent on the pruning mask. So the weight, the original weights are frozen forever. The only thing that you can optimize is the pruning super mask. How do they do it? They have a variant of gradient or stochastic gradient descent on the pruning mask. The algorithm, I would say, is not fully mathematically principled. It's kind of a heuristic, but it works surprisingly well. And what they find is that across a suite of networks and data sets and whatnot, what they can show is that you start with a random network and you can prune it to 50% sparsity. So, 50% of the weights will survive. But that prune network will not have tuned weights, right? It's just like the subnetwork that contains the information somehow about this predictor. And that predictor is as good as fully training the weights, all right? And when I saw this paper and I read it, I was completely blown away because this is, this was basically, at least for me, this was the first paper that kind of used a very, combinatorial, if you will, learning principle, right? Because now the only thing that you do, the optimization problem is a binary optimization problem, whether you keep or not a weight. And however, you can achieve this with this state-of-the-art accuracy across many tasks. And the main question that I will focus on theoretically for the remaining of the talk is whether this thing is true, right? So is it true that you can always approximate some target function by pruning random networks rather than training them? Under what conditions, right? So that's what I would like to understand. And if you take a quick pause here and you say, okay, that probably is trivially true, right? Because if you have a ridiculous network, like, I don't know, infinite width, everything will appear there, right? So somehow you can find everything in an extremely large neural network. So the interesting thing is, what can you achieve when you constrain the overparameterization, right? So that's what I would like to understand. But again, because I just want to make sure that everybody's on board, this is an important kind of like distinction between the original lottery ticket and what I will call the strong lottery ticket. I just want to make sure that everybody understands what we're trying to do here. So again, I don't care about sparsity here. The only thing I'm trying to understand is whether you can learn a function, whether you can approximate something by killing off weights. That's the only thing I'm going to do to the weights. I will not tune the weights.
I have a question then, Dimitris. Do you make any assumption on the random initialization of your weights in your network?
Yeah, so there's no assumption on the initialization. I guess you'll see in the proofs in a little bit, but the main thing that we would like them to do is at the very least have it in their support. Like, I want my random weights to be in the same range as the weights of the network I'm trying to approximate. So that's the only assumption that I need. But apart from that, what I will show is going to be true for essentially any continuous initialization. So there's nothing special about it. I don't know if this answers the question.
Yes, it does. Thanks.
Okay. All right. Anything else so far?
No, there's no other question in the chat.
Okay, good. So, all right. So I've been thinking about this problem since the paper came out, and I had a really interesting discussion with my PhD advisor, Alex Dimakis, and Kostis Daskalakis at NeurIPS 2018, or whenever the last in-person NeurIPS was. And we kind of like discussed the things related to how one could prove something, but it never led anywhere. And I was, I had it in the back burner on, how maybe we can prove something about it. And during that time, Eran and Gilad from Saisalef Schwartz group and Ohad Samir's group, they proved a version of what I was wondering whether it's true. So here's what they proved in this paper. They said the following. So let's say that you have some mystery network that you want to approximate, right? So maybe it's ResNet 18 that you used on ImageNet or trained on ImageNet or whatever. But you basically want to approximate the performance of some dream network that you like. And what you want to understand is the following simple question. If I were to start with a random network, okay, of some degree of overparameterization, maybe it's a little wider, a little deeper than the network whose performance I would like to approximate, could I prune that network to essentially get something that's as good as the original, all right? So that's what we would like to understand. And what they prove in this paper is that essentially, if you start with a fully connected network with ReLU activations, the depth of that network is L, the width of that network is D, then you can achieve an approximation by pruning as long as the random network that you start with has a polynomial factor, it's a polynomial factor wider than the original. So you start with a network that's, D wide, and if you want to approximate the performance of this network by pruning a random network, the random network should actually have a factor of D cubed L squared divided by epsilon squared more weights per, or more neurons, if you want, more activations. So it has to be a polynomial factor wider than the original one. And the epsilon factor here is kind of like how close do I get in approximating the function represented by this neural network, all right? So just a note on this, and I want to discuss this a little bit with you just to make sure that we're on board here. So this is an existential result. This does not suggest an algorithm. This says that, if you want to have, let's say the same expressive power as a ResNet, you can do this by pruning a random network, but that random network has to be significantly wider, right? So you need a lot of overparameterization. But this existence result tells you that not only you can find accurate networks, it tells you many more things, that lottery tickets exist at initialization, lottery tickets exist at later iterations, everything, basically everything that you want exists at initialization. That's what this result says. So it's very strong, right? It says a lot of things exist. But the only downside of this result is that it kind of uses this idea that if you have enough weights in this random network, by sole chance, you will find the weights of the original network, right? So basically this work finds what factor of overparameterization do you need so that this sort of idea works out. The idea that any network of size D by L exists in this sort of wider network. And the issue with this is that this does not reflect practice. So in practice, what they found in this Ramanujan paper is that if you want to approximate the performance of ResNet 34, like a fully trained ResNet 34 on ImageNet, these folks could prune a wide ResNet 50, so a network that basically had 6 times more parameters rather than a billion or whatever this number is, right? So in practice, it seems like you don't need that much overparameterization, and it's not clear whether this result is tight and whether the experimental evidence by Ramanujan are maybe a side effect of the type of architectures or the type of the data that they were using or whatever, right? So that's what we would like to understand. But again, I want to make sure that this makes sense, at least the result of Malak et al., whether it makes sense to you and whether you have questions. So again, this is an existence result. It says that pruning can approximate whatever you want as long as there is this degree of over-parameterization in the random network.
So Dimitri, there was a question which I took the liberty to answer in the chat regarding the width of this intermediate network, this middle network, right? How wide does it need to be? It's this big O quantity. And the question was, so if we want the error to go to zero, epsilon to go to zero, then the effective width needs to go to infinity, right?
Correct. Yes, that's right.
That's right. And there's a second question asked by Marwa in the chat. How small can the sub-network be?
Right, very good question. So in this paper, they guarantee that the subnetwork will be of the size of the original network. So it could be sparser, but it won't be denser. So, but again, I want to point out to the fact that here, the sparsity of the network you're trying to approximate is kind of like defining the sparsity of the network you're going to find by pruning. But this, of course, doesn't say anything on what's going to happen in practice, right? So sparsity is overlooked with regards to these types of studies.
But does it mean when they try to reobtain the same performances as a model network by pruning, will they try to, in the proof, will they try to basically find the exact same weights? And so like the pruned network, will it look like a copy of the initial network, or can it be like a different network that just happens to have the same performances or compute the same function?
Very good question. So for this proof, and the proof that I will talk to, these proofs are algorithmic in the sense that they use an algorithm to construct these networks, but they don't suggest an algorithm of how you would do pruning in practice. Coming back to the specific point that you asked, the way that this proof works is for every weight that so I assume Oracle access to every single weight. So somehow there's a magician that, she gives me the network, right? So this is the network. You can take it and tell me if you can find a subnetwork here that approximates it. So I do have access to every single weight. And the way that the proof works is that for this blue weight, I'm trying to find the blue weight that's kind of like as close to it as possible in L2 distance, right? Or literally you try to find a W that's as close to that target W, right?
Okay, so we do try to find an actual copy of the model network within the, okay.
Yeah. And, of course, more often than not, we'll be unlucky in the sense that you won't be able to find something that's exactly the same, but you will be lucky enough to find something that's as close as epsilon.
Just one last question. I don't see a term in delta within the expression of the weights. I assume that this is like with some probability we'll never be certain to find it. So I would expect that there should be a term in delta within the big O, no?
Yeah, there is. In fact, I don't know if the delta appears linearly, or I should say inversely linear or a logarithm, but yes, there is a delta. There's definitely a delta. But for now, we shouldn't worry too much about the delta, at least for this proof, or at least this statement. But I'll come back to the delta for the theorem I'll present for our results.
Sounds good. Thank you.
Very good.
Thank you, Dimitri. I don't see other questions in the chat.
Okay, great. So I already sketched the idea of the proof, but let's say that you have one network, and by one network I mean one number. And this is just a multiplication. You put x inside, wx comes outside, pretty trivial. But the idea of the big proof of that paper, you can highlight it very well from just this very simple example. So if let's say I have access to that w and I want to approximate it, and instead of like a single link, single edge network, I use this bizarre over-parameterization where I introduce an extra layer in the middle. Everything here is linear, okay? And bear with me for a minute because we will turn this into Relus in a few slides. But let's say that it's linear. You have this little diamond structure. On the left, you have random variables. The weights are just random, x1 to x5 or whatever number you want, or how many weights you want to sample. And then on the right, it's just a combining layer. So everything here is 1, 1, 1, 1, okay? In this very simple network, you can ask the question, how many x's do I need to have so that one of them is close enough to W? It's epsilon close to W. And this is a very simple probability question if the x's are uniform and they contain the support or the domain of the values of W. Let's say W is between -1 and 1 or whatever, and the xi's are between -1 and 1. if I wanted to only keep the one that's closest to W, I would need to sample 1 over epsilon random weights so that I'm epsilon close to that W, right? So this is like very standard, from a very standard union bound, super simple to prove. And the general theorem, of course, is much more involved than this, but this is kind of like the core idea that leads to this polynomial over parametrization, because you need to apply this idea for every weight in a layer and for every layer in the network, and kind of like everything multiplies together, and that's why you get this big polynomial factor of additional width required to obtain this pruning existence result. So this poly 1 over epsilon dependence is unavoidable. If if the approach you follow is this pruning weight by weight type of algorithm. Of course, the question is how can you improve on this? This is what we did in the follow-up paper. So we have an exponential improvement in the over-parametrization. We prove that, in fact, you don't need to have a polynomial extra width. You can only add a log factor to the width. So you start with you start with D, that's the original width of the network, and you multiply that with a log DL over epsilon. To the question with regards to the probability, this will be a high probability result. The delta appears in the denominator inside the logarithm, so it's not too bothersome. But the point is that we can promise that you can approximate everything, not just this particular D by L network. Any D by L network exists approximately within a random network whose only log factor wider. Okay, so this is the statement. I will be more precise about how we build this, but I just want to make sure that this makes sense to you and it's understood by everybody.
Any questions from our audience?
Again, if I know that this idea of existence is a little bit weird because you assume access to this network, but this is just saying that even if you don't know nothing, you start with a random network, there's already the promise that you can find everything there. You don't have to worry whether, it's not a side effect of the architecture or the data set or whatever. Everything exists in a random network without even having to tune the weights. All you need to do is find a sub-network that does what you want.
Right. I think
Okay.
the message is clear. I don't see further questions.
Okay, good. So
sorry,
yes.
I just assume if you were to take another multiple for the depth, like 3L or 4L, you will be able to improve the depth constraint as well, right? Because you'll be able to connect more, like to use more layer to reproduce the weights in the initial network, and I assume that the bound will improve like drastically if you increase more the depth.
Yeah, so the depth here is only 2. The reason for that is the diamond structure that you saw before. I'll come back to it. This is kind of fundamental. Like to approximate one weight, you need sort of like which think of it as, I guess, I don't know, one layer thingy. You need 2 layers. So that's where the 2x comes from. Yeah, but it could be the case that, if you were to make this deeper, you could get something out of it. Yeah, I don't know.
This is my point. It's that what I understand from the diamond structure is that basically the diamond structure shows you how many paths do you have between the 2 weights to by chance find like a combination of weights that has the weight that you're looking for. And if you increase the multiple of the depth, that multiplies like with a combinatorial factors that will multiply the number of paths. And so that should multiply also the number of chances that you have to find this exact weight. And that's why I'm expecting that maybe we can find like similar bounds, but better for different multiples.
That's a good point. I would like to discuss with you a little bit offline, because we have a proof for the case where you use binary weights, and you can kind of like prove the same stuff. I'll see if I have time to talk about this, but we use exactly this idea that like the width, like, it's not random numbers, it's like random binary stuff, but like for random binary weights, the multiplication thing that happens across across depth actually increases the capacity of the network. So what you're saying makes total sense. It would be interesting to see to what extent you can improve. You can maybe even trade off the width for depth. But I think what you say makes total sense to me. Yeah.
Thank you,
All right,
Charles.
thank you.
Thank you, Charles. We have one more interesting comment on the question in the chat. You basically have those two algorithmic constructions, okay, for those two different levels of over parametrization. Do you expect or know that these two approaches will lead to different sparsity guarantees or different levels of sparsity?
They will. In fact, yeah. This the Malak et al. Construction leads likely to sparser networks by log factor sparser than what I will talk about, because you'll see in the next step that sort of the algorithm that approximates every weight in our case combines multiple weights. So you kind of like you do need higher sparsity in our case to get this. So the answer is yes, that basically our work does lead to denser networks than the Malak et al. Work.
Okay.
So in fact, you know what? I think there's an interesting interplay. This is kind of like tangentially related, but somehow the algorithm I will explain is harder. It's a subset sum algorithm, and there is this balance between, if you are not willing to have a very wide network, then you have to be smarter about the algorithm, right? So you have to like spend more compute. Mm-hmm. But if you're like generous with overparameterization, a very simple algorithm gives you the approximation. So there's an interplay here between overparameterization, the computational complexity, even when you approximate weight by weight, and then the sparsity of the algorithm, or the sparsity that comes out of the algorithm. So these things are interrelated, and they're not very well understood, and I'm extremely interested in discussing more about this.
Just to make sure I understand something well about this, in both cases, I expect that the number of parameters from the pruned network should be about twice that of the original network, right?
So no. So for the first one, it's going to be twice as many. The second one may be up to 2 times log as many. So it could be logarithmically more the parameters.
So you do not try to reproduce exactly like the edges, because from my understanding, like each edge of the initial network will basically have in the pruned network one more step, like one more intermediate neuron,
correct.
Which will like create just like 2 parameters instead of 1, or like is that not what you're doing?
Yeah. So this goes into the proof, which I will talk in a little bit.
Okay,
and the
sorry.
main point. No. This is a great segue, because the main point here is that we will exploit somehow the fact that these activations actually do some computational work. It's not just like trying to find a weight that's similar to the original weight. You can actually exploit the fact that these actually do combinations of stuff, and then we are going to use this idea of combining weights to approximate one weight. So it's not going to be a one-to-one approximation. Yeah.
Okay, so you can have much more than twice more parameters. Okay.
Precise. Yeah. So let me go to the actual proof and explain how this works. So now the idea is the following, right? So the previous proof said, okay, have a bunch of random variables on the left side. And again, this is going to be a combining layer all once. And our suggestion is like, instead of, this layer actually does like it adds stuff, right? So it is taking a summation of the weights in the previous layer, or whatever comes from the previous layer. And that actually may help you a lot, because there's like, exponentially many possible ways that you could sum these variables. And that is what leads to an exponentially higher capacity once you view the pruning or the algorithmic part of this proof from the perspective of the subset sum. So now we're asking, if I were to find the best subset across those random variables, how would that help, right? So again, the idea here is that you pick a subset of the x's, and then those x's are combined out here, right, on the second layer. So here, pruning corresponds to finding the best subset. And you can think of this as a batch version of single parameter pruning, right? So it's not like you're not pruning weight by weight. You're kind of like, you're being a little smart about like pruning in a batch manner. So you're looking at many weights, and the next layer, you're like, okay, how can I prune this so that it approximates that little W weight? And the main question is, so let's say that you can solve this subset sum, forget about computational constraints. But if you do this, you can ask, what do I need to get the same approximation guarantee? Like how many of those random variables do I need so that I'm epsilon close, so that the best subset is epsilon close to the original weight W? That is the probability question I would like to ask now. This was solved by Luker in 1998. So you can write many papers by being great at Google Scholar, and this is what happened to me for this paper. So at Google Scholar page 55 or whatever, you find a very interesting paper about random subset sum instances that Luker wrote many years ago. And basically, this is what he proved. So this is exactly kind of like what we want. So he said the following. Let's say that I have uniform random variables over -1, 1. And I combine them. I can take every possible subset. Then with exponentially high probability, both in the number of weights, but also the accuracy, I can basically find something that's epsilon close to whatever target number. So basically, simplified, what this says is that every number in a fixed domain, fixed range -1 to 1, can be approximated by taking a subset of log 1 over epsilon random variables. So you sample without knowing anything, right? So you sample n random variables, that n is log 1 over epsilon. And the promise that Luker gives you is that you can find a subset of those log 1 over epsilon random variables that comes epsilon close to any number you want in this -1 to 1 range. Right. So this is an exponentially better result with regards to like how close you can come to a single weight, because you're taking advantage of this computational power of the summation, right? So I mean, you have exponentially many choices compared to like the previous technique by Malak et al, where you only look at sort of the closest weight when you sample. Does this make sense to you? I just want to make sure that this is clear.
I have a question for you.
Yeah.
It seems to be a bit mysterious to me that you take the x1 and xn in -1, 1, but you approximate numbers in -1/2, 1/2.
Yeah. So the reason why this happens is you kind of want to make sure that there is enough, right? So you want to make sure that there's enough stuff on the left and right of those numbers, right? So if you're not, if your range was like -1, 1, and you were trying to approximate something between -1 and 1, then you wouldn't get kind of like a uniform probability result for all the individual numbers in terms of approximability. You know what I mean? So like if, you would have worse approximability for the edge cases, and then the closer you were going to like whatever, inside the range, you would be better, right? So that's why you do it. I would say operationally, that's not too big of a deal. If your weights are between -10, 10, that means you have to use random variables between -20, 20. But this is why this happens. I don't know if there's a lower bound to this. Maybe you can do something better, but yeah, I guess I'll have to read the paper by Luker a little bit more closely.
But so because if you would ask for something like -1 plus delta and 1 minus delta,
yeah,
you would get basically what, a worse constant?
Yeah, I believe in his paper, without, I may be wrong, but I believe in his paper he does talk about this 1 minus delta and -1 minus delta and 1 plus delta or whatever. So he adds a little bit of fudge on left and right of his range. But yeah, I think you only need a little bit. You don't need like, half is here just for, making the numbers prettier.
I see. Okay, thank you very much.
Good. So, okay, so let me tell you how you can make this into a neural network, because Luker did not make, this proof is not for neural networks. This is for this diamond structure where you I want to approximate a number, W, and have the random weights on the left. These are the n random variables. I have the summation on the right, and you prune on the right because this is, where you choose the subset. So the theorem from Luker, this is the picture of the theorem, right? But this is not it's a linear network, it's not a ReLU network. So we want to transform his proof or his theorem into one that's about ReLU networks. And this is how we do it. So we take the weight W and we split it. So, if X comes in, WX comes out, you can simulate this by two little ReLUs. So, you can have a ReLU whose input weight is W and output weight is 1, and another ReLU with -W and -1 in the output. And these two things are equivalent. This seems a little weird, but it will allow us to prove something about fully connected networks rather than these weird diamond linear networks. And now what we can prove is essentially a version of Lucker's theorem where we say we can approximate this network by pruning this blue part of an overparameterized network. So now everything here is random uniform on the left and on the right. So the A's, C's, B, whatever, all these variables are uniform random variables. We prove that if you have log 1 over epsilon ReLUs, you can prune on either left or right side to get something that is epsilon close to this blue subnetwork here, and similarly for the negative part of the ReLU. So there is a very simple generalization of the Lucker theorem that essentially still holds for ReLU networks, or for this little ReLU network. The only thing that you need is that basically the product of the distribution of the input weights and the output weights needs to contain in its domain the possible range of weights that you're trying to approximate. That's the only assumption you need, but this works for any distribution you like: uniform, Gaussian, Laplacian, whatever is your favorite initialization. But this is kind of like the gadget that is very important to establish the main theorem that we have for arbitrary fully connected networks with ReLU activations. And the way that we do this is, you cannot start with the one-dimensional function, one-dimensional product. We saw that you can basically prune this fully connected ReLU network to approximate W times X. You generalize this by applying it to every single coordinate of this sort of d-dimensional input function, just the inner product. You apply this on every single of the coordinates of W here. You get a very similar result, and then you can make it into a matrix form. Similar guarantees for the error and how much overparameterization you need. And the last thing that's left to do is basically apply it for every single layer because of the smoothness of the ReLU function. There's very simple operator norm bounds you can apply, so you can essentially get the result that I promised you in the beginning of this talk, which basically says I'm approximating a function fx. I have a network that's fully connected, in this case, with ReLU activations. The network is random, so these M weight matrices are completely random. S are the only matrices that I'm allowed to choose. They're binary. I either choose to prune or not a particular weight, and I will promise to you that I can come epsilon close to that function x for any single input x that's bounded. And this bound, we bound it by 1, but this again appears in a logarithmic fashion inside the overall overparameterization bound. But anyway, this is kind of like roughly how we prove the final result, which I will state again a little bit, but I just want to make sure that this makes sense from a high-level perspective. I understand that I skipped over many details, but hopefully the high-level idea is clear to many of you.
Thank you, Dimitri, for the clarity and the time for questions. Yeah, anyone from the audience, don't be shy. Now is the time to ask. I see someone typed a question in the chat, and I'm going to relay it. Why not make the signs as an explicit input, and then the upper and lower symmetry part can be reused? Sign changes only require a fixed amount of nodes. Is the...
I don't understand. Yeah, I'm not sure I understand the question.
Not sure I fully understand either. So there were some signs, I guess, and when you were trying to discuss the equivalence between...
Oh, this one.
Right. Plus 1, minus 1. Maybe Pang, maybe that's what you're referring to?
So I guess the one thing I want to say is that, we're not being very smart about, this being in one, and we're trying to approximate it, and, maybe you can do something better, because arguably that's probably true. we're being very, rough in the approximation. You can arguably optimize these bounds. I don't think significantly, because I'll show like a lower bound where, the logarithm in the overparameterization is sort of unavoidable, but you can probably save some constant factor by being a little bit smarter about how you create those gadgets.
Right. Okay. Maybe Pang can get back to us with his question at the end of the talk, but I think that's a good point about the logarithm Is there a lower bound that says the logarithm, you cannot shave the logarithm?
Yeah, so the lower bound that we prove essentially tells us something about the log 1 over epsilon part. So the overparameterization, if you remember, has a log, and on the numerator of the fraction, there's the depth and the width appearing, and then the denominator, there's the epsilon, the approximation error. So that log 1 over epsilon is unavoidable, but the log DL may, you may be able to avoid. So, again, there's this DL here, right? This, I'm not sure that you need, but this epsilon you definitely need. So there is, there's a very simple sphere packing or, function packing argument that applies to just like one layer neural network with linear activations where you just, you can't fit more functions than, you can't approximate more function than, a given number when you constrain yourself to be only of width log 1 over epsilon. So in that case, it is fundamental.
Right.
That's how many functions you can pack somehow in a matrix. But there's nothing that we can say with regards to this DL parameter in the log.
Mm-hmm. Okay.
All right. So yeah, I just want to recap here. I didn't tell you anything about good algorithms to prune networks. I only told you that there is nothing that stops you from learning by pruning. You don't need to tune weights. You can just kill off weights and you can still be able to get something that's extremely accurate. Essentially, we're substantiating theoretically the results by Ramanujan that did this experimentally, and we saw that this is universally true, meaning that the expressive power of pruning is good enough. You don't need to tune the weights individually. You can just use the initial value. And this is true for any initialization. Some are better than others, as I will tell you in a little bit, but this is basically the main result again. So I have maybe 5 more minutes, Yanni.
You have
Or 0.
Another half hour if you want. We have another half hour in the meeting. Take
half hour. I don't want to bore everybody on the call. I'll maybe talk a little bit more, and then we can switch to discussion mode.
Exactly. Take your time.
Oh yeah. So okay. So very briefly, one experiment that we ran, and I'll just put everything here. Don't read this. I'll just tell you what happens here. So the ability to prune a network to high accuracy significantly depends on the way that you widen it. Remember that we said that to get the accuracy of whatever, a ResNet 50 you need, or a ResNet 34, you need to use like a wider ResNet. The way that you widen actually matters a lot in the accuracy of those pruning algorithms. We ran a specific experiment. I'll be happy to go into more detail after this, after the talk concludes. But kind of the main point is that I have many choices about widening the network. One very simple choice is I can just keep adding, convolutional filters per layer, or like making the fully connected layers just wider by adding more activations. Or I can be a little smarter and I can, replace every weight with, those diamond structures, right? Remember the weird diamond ReLU structure or linear structure that I told you before? You can do this and create a network that's equivalent in size, have something that's just wider, has more convolutional filters, or have something that replaces every edge, every parameter in your network by this weird diamond network. And it seems to be the case that pruning algorithms like these diamonds. I don't know why this happens, but they tend to be more accurate and give sparser networks when you're a little smarter about how you overparameterize. And there's a lot to discuss here, but keep just one thing, that the way that you overparameterize matters a lot in the performance of pruning. And we can come back to this point in a little bit. The other cool thing is the following, that the amplitudes of the weights actually don't matter at all. So let me tell you about the thing that excites me most lately. So in the original paper by Ramanujan, they found, so they had the baseline, this was baseline ResNet 18 and ResNet 34 on ImageNet. This was counting number of parameters and the top one accuracy, whatever. So they have 2 ways of pruning, same algorithm, they change the initialization. The first experiment is with binary initialization. So every weight is like ±1, but with a scaling, which doesn't matter at the end of the day. and they try Gaussian initialization, and to everybody's surprise, binary networks, like, pruning binary networks, was actually more accurate than pruning networks that were initialized with Gaussians. This still seems pretty crazy to me. I don't understand why this happens. But this is something that we're trying to study in my group, understanding sort of the expressive power of, pruning binary networks. I guess there's a benefit in using binary networks. They're hardware friendly. They're more compute and memory efficient for many good reasons. It was unclear whether sort of similar results as what I promised to you about, continuous distributions also hold for, networks that have been initialized by plus minus ones. So what we prove is something very similar to the original proof, that you can still approximate everything you like as long as that thing is a D by L neural network. So you started with a network, again, that has the width is D, the depth is L, or whatever. You make the whole thing logarithmically wider this time, so you do need the width here, and you need the logarithmically deeper and logarithmically wider. So you do need this logarithm also when you kind of like make this network deeper. And this has to do with a question that was asked before, that somehow depth increases your ability to express individual numbers. I can come back to that. But somehow the main point is that weights are not important, or amplitudes are not important. All you need are the signs. And this result also improves exponentially a polynomial width result that appeared in iClear 2021. We haven't published our paper yet. I don't even think we have it on arXiv, but my promise is that you can basically establish a very similar existence guarantee for binary random networks. Any questions on this?
Yeah, I have something I'd like to get clarified. So before you went into the binary world, right? You had everything was a factor of 2 deeper because you needed those diamond structures. And now you have this extra order log D over epsilon, right?
Yep.
I see. Does it mean you create different, more complicated structures, diamond structures that are logarithmically deep?
So precisely right. So to get the same existence result, we need a new gadget. Remember the little gadget with how we approximated the ReLU with like a diamond ReLU function or network. So to do this with binary networks, you need a weird gadget that is log deep and log wide, because essentially what we do is we do a binary expansion, right? So we approximate every number by its binary expansion and threshold to accuracy epsilon, and to create sort of these weights by combining binary numbers, you need the depth. So, but it's exactly why we have this extra log factor.
Okay, that's very clear. Thank you. And Gauthier has a question also.
One thing I wanted to add here is that this does not explain the fact, very curious fact, that in practice, binary nets perform better. That's a mystery. I have no idea why this happens.
Just happens to be the right type of regularization here, maybe?
Yeah. So one could argue that so I think now it's fair to say that initialization is a tuning knob, right? So your algorithm actually depends on how there's nothing else you can do on the network. So you might as well be smart about your initialize. And one can argue, Gaussian is too random, right? Why would you need weights all over the place? Maybe just binary helps. But that, to me, like that explanation I just gave to myself, is not intellectually very deep. I don't think that this is explaining what's going on. But I do think that one can be smart about initialization, since it does seem to matter a lot here, much more than traditional training.
Okay, let's go to Gauthier's question. And I think more people might be interested in discussing this point here on the why we get better performance. And let's do that. Let's do that at the end. Gauthier, your question.
Yes. So Dimitris, thank you very much, first of all, for this great talk. Honestly, that the lot of math and a lot of interesting results. I loved it. I have just a question about your title, almost. Learning is pruning. But it seems that it's more like pruning is approximating than learning, or maybe learning is approximating for you.
Yeah, that's a good question. Or a good point. So, in practice, or I should say experimentally, we do see that you can get identical performance with regards to the classification accuracy. Although our results here are for regression, you can turn them into classification by using some margin assumptions. But somehow, once you're epsilon close to in function value to the network, then you can prove that with regards to the classification accuracy, you can be exactly the same. But I think it's a fair criticism that you always come epsilon close, and I would argue that this is more an artifact of our analysis that operates on a weight-by-weight basis. You can arguably get something that is better, more accurate, if you were to think about this from a more functional perspective, or kind of like a combination of two, right? So we are, two. I don't know if it's fine grain or coarse grain, but we're like zooming into the tiniest sort of element of the network, right? But I don't think that this is necessary. And by looking at what is the internal representations of the network and just trying to approximate those rather than individual weights could potentially lead to something that is truly matching one function with the other.
Thanks.
Thank you, Dimitri. We
Cool.
have another hand raised by Marwa. Go ahead, Marwa.
Okay.
Hi, I had a question not about the binary presentation. I was wondering for the results, experimental results by Ramanujan, how did they actually do the pruning?
Yeah, so they use an algorithm that is a variant. So think of the following. Okay, I'll tell you the high level of the high level idea of the heuristic. It's not the algorithm, but this is roughly how it works. Every weight is associated with a survival score. Okay, so think of the score as between 0 to 1 or whatever.
Mm-hmm.
The algorithm at every iteration uses something similar to backpropagation to compute essentially a gradient, and you look from that gradient how well it is aligned. The gradient for weight I, how well is it aligned with that particular weight somehow. If the current weight, if it's on and it points to the right direction, you increase its survival score. If the weight is in the wrong direction, if it's on and it's in the wrong direction, you decrease its survival score. And then at the inference cycle or during inference, for every layer, you keep the weights that have the highest survival score. So essentially, you keep scores for the weights and you update them with a gradient-based algorithm, and you keep the top percentage of those high-scoring weights for every layer. So that's a very high-level idea of how this algorithm works.
Okay. All right, thank you.
Thank you, Marwa. And we have one last question by Charles, and then we're going to let our speaker proceed.
Yeah, I just, and I think it connects to the previous question, but that means that the fact that binary nets perform better could purely be due to the choice of algorithms that they use to prune, right?
Yes, yes.
But, okay, so just regarding the sparsity of the pruned network, if I understand correctly, technically it could be that we approximate the target network without doing any pruning, and we could have like a full network at the end. If by any chance, when we look for the subsets, it's always the full subsets that approximate correctly. Depending, I don't know exactly how the theorem that gives you the probability to find a subset works, but depending how it works, perhaps we could achieve like a probability distribution of the remaining number of parameter after looking for. It might not be interesting at all, I guess, because even if you have no pruning at all, I guess it's still.
This is an interesting observation. So you could define a distribution on the sparsity, on the degree of sparsity for the subset sum algorithm, and we did this. And the interesting thing is that we found that like if you were to actually apply, again, you should never do this algorithm because it implies that you know the first network. So you have to train first and then do the approximation. Yeah. But if you do this, so we did this, again, doesn't make sense, but we did try it. And we saw that if you were to solve the subset sum for every weight, more often than not, we would use like, if you had, log 1 over epsilon in our case was like 10 or whatever. out of the 10 random weights, we would use half of them. So it was not sparse.
I mean, that makes sense. If it's basically if the subsets are independent and it's just like every subset has an equal chance to be a solution, I guess in average the random subset will have an expectation of half of the element of the subset. So that would make sense that you keep half the parameters at the end. And it's interesting that there is nothing.
Yeah, in fact, I guess the other point is that if somehow you were to prove that all the sparsity, like, there's a concentration of the sparsities to, let's say, around 1 or 2, you would also prove that subset sum is easy for Gaussians, which may be true, I don't know, but like, it kind of like has computational complexity implications, so it's a little bit of a tricky landscape.
I see. All right, thank you.
So I want to say something, but why don't I conclude here? I have a slide for conclusions. I will skip the steps for the proof. Yeah, I want to talk about open problems. I'll skim through them and kind of like close with a final slide. There is no provable pruning algorithm, number one. Even if you were to try to prune, I don't know, linear classifiers, we have no idea how to do it. The current algorithms are very heuristic. They're not principled. We don't know how to prove that SGD converges for like resonance or whatever, but at least it's a very principled algorithm. You take the gradient direction to minimize the loss, right? It makes 100% sense. We don't have this for pruning. Like, there's no SGD-like algorithm in that sense. It's a very interesting area, at least for me. And the thing that excites me the most is that, this is a combinatorial problem, right? So, the Ramanujan paper suggests sort of, it's a relaxation to the combinatorial problem, but there is a ton of like literature in combinatorial and grid optimization that they don't use backpropagation at all and can potentially lead to a very interesting learning paradigm. And I think scientifically that has a ton of interest. Just like, kind of like break the walls of SGD, just go beyond and see what else is possible. And this is something that we've been thinking very hard the past, I would say, year, kind of like a backpropagation free algorithm for pruning. This is completely open. And I have some ideas that I can share with you at the end of this talk. The geometry of pruning is also very interesting because, if you think a little bit about it, is, you throw all those, every single hyperplane here corresponds to an activation. On the left, you have some, you have plus. On the right, you have minus. At the end of the day, you have an arrangement of hyperplanes. Every cell has a different label or whatever. And what pruning does is it keeps a subset of those hyperplanes that kind of like, maximally comes close to whatever thing you're trying to approximate. There's a very interesting connection with the literature of arrangements of hyperplanes. This is a very old, literature in computational geometry that people have been studying, for many years. And there's some interesting results that, we've only started to, discover lately. So, very interesting connection to that area. I still don't have many things to say here, but I think this has a lot of potential for a lot of cool math, but also algorithmic developments. I will skip this. There's a lot of cool applications. I can talk about them offline, but I just want to conclude with basically a couple of things. What I proved is a sort of like it just says that within a random network, you can find anything and you don't need to over-parameterize too much. You can do this only by pruning without tuning the weights. This also proves stuff that, basically you can prove that everything exists. This can be used to prove that at initialization, you can find lottery tickets, but it's, of course, it's computationally hard, or we don't know how to do it so far. So, the limitations of the original IMP algorithm is not because of existence. It's an algorithmic bottleneck at this point. I don't know if this is a computational bottleneck. Maybe it's not possible to do it, but, I think it's worth thinking more about. I didn't tell you anything about, what happens if you were to combine a little bit of training, going back to the question of like, you leave that epsilon of error at the end, you could train a little bit, and that epsilon can go away, right? So you can prove interesting things with regards to existence if you allow a little bit of training after these pruning type of existence results. There's this whole idea of architectures that are amenable to pruning. And again, the thing that actually excites me the most is backprop-free approaches, because I think, again, pruning opens a whole host of, different algorithmic techniques that you couldn't apply to traditional whatever weight training. And yeah, I'll just go back to this slide and conclude here.
Thank you, Dimitri.
You are welcome.